So in the last week, we have came to know about potential energy surfaces, how to do geometry optimization, and how to do second derivatives Hessian and get frequency and IR and Raman spectra out of it. The thing what we completely skipped in the last week was the thermochemistry. So calculation of frequency additionally leads to the information about thermochemistry. So up to now, whatever we have discussed is only the electronic energy. In most of the experiment is performed not on a single atom or a molecule, but a collection of atoms and a molecule. So to access the properties of that kind of system, you need to take help from statistical mechanics, which connects the behavior of individual atoms and molecule to that of the bulk. So this week, even before going into the theory, we are going to do in this class is to compare the relative free energies of gem, trans and cis butene. We are going to come which is free energy, because up to now we have only talked about the electronic energy of this one, and we are going to do, so the experiments are available in the room temperature and 1 atmospheric pressure. So up to now whatever calculations we have done, there was no information about the pressure, and there was nothing which was about the temperature was only 0 Kelvin. So the temperature and pressure effects are actually now we are going to take care in our calculation, and this is often brings you to the discussion. And I often ask this question to my students that, okay, you are talking of temperature, Schrodinger equation does not have any temperature. It's done in 0 Kelvin. So then what temperature you are talking about, and what entropy and what enthalpy you are talking about. Now the subtle part of that, to do this thermochemistry, although we use electronic energy calculated from Schrodinger equation, to get the statistical mechanical quantity, to get to the thermochemistry, what we use is a thermochemical analysis based on statistical mechanics of ideal gas. So these are calculated from classical partition functions, and these are calculated by using the approximation that your molecules are actually behaving like a classical particle. So the assumption, before making any approximation, the assumptions you take is that the electronic state is orbitally non-degenerate, so that there is only one state. There is no thermally accessible electronically excited state. So at the temperature what you are doing, your excited states are no longer possible to access, and the hindered rotation indicated by low frequency modes are not treated as such, but treated as vibration. So some of the low frequency modes are generally problematic thing. You are considering them as that can also be considered as some hindered rotation, but here in this analysis we are going to treat it as vibration, and this vibration is mainly an harmonic. All the equations used are the statistical mechanical equation are used for ideal gas, and all the vibrations as we discussed are strictly harmonic. So ideal gas assumption means molecules in the gas phase are assumed to be non-interacting except during elastic collision. So they are not like there is an interaction, and the gas particle moves randomly in all directions and occupy a large volume compared to their size. So the partition functions are derived using canonical ensemble. That means it has a constant volume, constant number of particles and constant temperature. So for an ideal gas, the total partition function is a product of contributions from the transitional, rotational, vibrational and electronic state. So the transitional partition function we generally calculate by assuming like a particle in a box model, and if you do the calculation, this is the final form. For the rotational partition function, we consider the Schrodinger equation for a rigid rotor, where for linear molecule this is the formula, and these are the formula for the nonlinear molecule. And the vibrations we actually take an harmonic oscillator consideration, and for electronic partitioning function we take this form of the partition function, where Gi is the degeneracy of the electronic level and Ei is the corresponding electronic level. At typical temperature for most of the molecule, the ground state dominates the partition function, because the energy gaps are so high that in the normal temperature it is not possible to populate the excited state. For atoms and molecules which are closely spaced energy level or at very high temperature, contribution from multiple state must be included. And of course, these approximations allow us to have accurate estimations of enthalpy, entropy and Gibbs free energy. And of course, if you get the Gibbs free energy, you can compute reaction equilibrium constant, predict spontaneity, and this can also enable calculation of many thermodynamic property like heat changes during formation, combustion or dissociation. So, all these calculations when you will perform in ORCA, they will be performed using the temperature 298 Kelvin, pressure of 1 atmosphere there. So, the total mass, of course, it will change from system to system. So, and they will be used using this RRHO is rigid rotor harmonic oscillator approximation, and frequency which is below 1 centimeter inverse will be considered as 0, or they will not be considered as vibration. So, my internal energy will be considered as electronic plus 0 point energy contribution plus vibrational contribution plus rotational contribution plus translational contribution. So, where E electronic is the total energy from the electronic structure calculation, and this is the summation of kinetic energy, nuclear repulsion, electronic repulsion and nuclear electron attraction. Whereas EZP is the zero temperature vibration analysis from the frequency calculation, that is the 0 point energy calculation. The E vibrational is the finite temperature correction to the EZP due to the population of the excited vibrational state. E rotational is the rotational thermal energy, and E translational is the translational thermal energy. And if you add the KVT with this one, these are called, give you enthalpy. And if you also consider the entropy contribution, the entropy will also have electronic contribution, vibrational contribution, rotational and transitional contribution. You can get to what is called a free energy in this case. So, let us now go back to the example what we were talking about. And but before going that, so whatever we had discussed in the ORCA output file, this is what it will look like. So, this is the electronic, this is the inner energy, what is electronic plus ZP plus vibrational plus rotational. So, you can see their contribution. In comparison to the electronic energy, the rest of the contributions are actually quite small, and highest amount of the contribution actually is the 0 point energy contribution. And generally thermal entropy contribution, where KVT is a Boltzmann constant, is also quite small. And among the entropy contribution is generally the higher contribution is the translational and rotational entropy, because the states are non-degenerate. Most of the cases we will discuss. So, the electronic entropy will be 0 and gives free energy. You can calculate by doing the entropic and enthalpy correction. The good thing about ORCA output file is that the gives free energy minus the electronic contribution is already plotted. So, this helps you to use this like the other contribution except the electronic energy calculated from a lower level of method and add it with a higher electronic energy calculated at a much higher level of method using larger basis set, more accurate method. So, that means the other contribution to the energy, the statistical contribution to the energy what you are calculating from partition function, that does not necessarily be taken as the same level where you are calculating the electronic energy. So, let us now go to the example what we are talking about, and we can see how this gets manifested into. So, this is my test system. So, it is gem-butene, trans-butene and cis-butene. So, we have to draw the structure, we have to optimize them, and then we have to do the single point calculation. For optimization, we are going to use BP86 DEF2 SBP, and single point calculation we are going to use DEF2 QZBP. Now, let us see the level of calculation one by one. So, first start with the optimization. So, let us start Avogadro. So, let us start with the zem-butene. Now, I make the bond order to be 1 and replace this one by CH3. And I can make an ORCA input file. RI BP86. I want both opt and freak. So we can write it as compute here. Again, I'm opening with mobile extreme because we can see the when the optimization is running. Let me submit the Gembut job, and by the meantime I can generate the trans isomer. Maybe I should start with a new Avogadro. It's a double bond. Let's first make the trans one. So this is single and this is a trans one. If I go to the extension, optimize the geometry, and I can make the Orca input file as RI BP86 opt frick. Transmute. So let's see how the previous job is running before I submit the new job. So this essentially means the optimization is converged. Now it's trying to do the Hessian calculation. So now let's wait it to get finished and then we can submit the trans job. It's done. It's taken 2 minutes 45 seconds, so not a bad one. Let us submit the trans butene dot job. Okay, by the time the job is running, what we can do is that we can also make the input file for the sys1. So carbon double bond, now carbon single bond, so we've optimized it. Now we can make the input file. RI BP86 opt is cis but. Let's see how our trans job is going. So this is also the frequency calculation is going on. So if we open the gemboot.out file, so it will start with the optimization. So here is the part which we actually not discussed, this one is the internal energy, is the electronic energy, 0-point energy, and all the other contribution. So these are the total correction and total thermal energy, total enthalpy, and these are the entropies. So these are the final entropy term, and total final gives free energy, and gives free energy minus the electronic coordinate. So we'll come back to that. I believe our other job is finished, so we can go to now the cis one. So I prepared an Excel file like we have done in the previous cases. This file does not exist, we can make one. So this is gem. Okay, first let us write the method. And this is electronic. This is G minus EL, and this is G, and this was is gem. Maybe we should give it a nice color maybe. So this is trans. This is cis. I wanted to check which one is written in the order. It's relative del G. We should change the color. and this is also relative del G. So we are all set for the calculation. So this is the total electronic energy. This is the Gibbs free energy minus the electronic contribution. So the total free energy is this plus this and of course we are talking for this isomer. So this will be, anyway it will be 0, so it does not matter. Now similarly I can do the trans one. It's transmute dot out. So for this one also the electronic energy is 6.98. Oh, this is not the electronic energy, this is the electronic energy 10320. And the Gibbs free energy minus the electronic contribution is this one. So if I add them together I will get the G. And if I want to consider the relative value, this is this minus this. These are given in kilojoule per mole, so we will convert it into kilojoule per mole, but let us first before this C's job is running, let the C's job get finished and